Welcome to the History Maps podcast. So think about a merchant in the early medieval period.
Okay.
They are traveling with a caravan deep in the arid expanses of the Khwarezmian Desert.
Which is thousands of kilometers from home.
Right. And the sun has just set, the temperature is plummeting, and it is time for evening prayers.
A daily requirement.
Exactly. But to fulfill this fundamental obligation, you have to know exactly which direction to face.
Not just roughly south or, generally west.
No, you need to align your body precisely toward a single stone structure.
The Kaaba.
Right, located in Mecca. And the really interesting part is that you have to do this without a compass, without a printed map, and definitely without a smartphone.
It is a massive logistical and mathematical challenge.
It really is. And today we are going deep into the evolution of geography and cartography in the medieval Islamic world.
Spanning from roughly the 9th to the 16th century.
Yes, we are going to examine how a vast, interconnected empire solved the problem of knowing exactly where they were.
Moving from very localized navigation to, well, highly complex mathematical models of a spherical Earth.
Because the problem you just mentioned, finding the direction of Mecca from any point on the globe, is really the catalyst for this entire era of scientific inquiry.
It absolutely is. That sacred direction, it's called the Qibla.
Right.
And in the very early years of Islam, when the community was mostly situated in and around the Arabian Peninsula, determining the Qibla was a relatively localized issue.
Because you were relatively close to Mecca.
Exactly. But as the Islamic Empire rapidly expanded across these vast distances, stretching from the Iberian Peninsula in the west all the way to the borders of India in the east, the geometry of the situation became incredibly complex.
You're not just looking down a trade route anymore.
No, you were trying to account for the curvature of the Earth over thousands of kilometers.
And according to the sources, this necessity birthed two parallel but very distinct approaches to understanding physical space.
Right, one that relied on the immediate observable natural world and another that relied on theoretical mathematics.
The documentation categorizes these as folk science and mathematical science.
Yes.
Let us start with folk science, because the way it is described feels almost visceral. It did not involve astrolabes or complex trigonometry.
Not at all. It relied on the physical environment that a traveler or a farmer would experience every single day.
So it was rooted in pre-Islamic Bedouin traditions.
Correct. For generations, nomadic groups in the Arabian Peninsula navigated the harsh desert environment by developing this acute, highly localized understanding of their surroundings.
Like they memorized the rising and setting points of specific stars.
Exactly. And they understood the seasonal patterns of prevailing winds. So when the requirement to determine the Qibla arose, the natural inclination of the broader populace was just to adapt these existing practical methods.
They didn't need a mathematical proof.
Right. They needed a reliable rule of thumb.
I want to look at a specific example of this because the level of physical detail is really notable. There was an 11th century legal scholar named Ibn Suraka.
Oh, yes. He spent time in Mecca.
He did, and he wrote down a set of instructions for people living in different regions on how to find the Qibla.
And they are highly specific to bodily orientation.
Yes, like if you were an inhabitant of Iraq, his instructions were incredibly detailed.
Ibn Suraka's method is really the perfect distillation of folk astronomy. He instructed that a person in Iraq should position themselves so that the stars of the constellation we know as the Great Bear rise and set behind their right ear.
Behind their right ear, okay.
Yes, and simultaneously, a specific group of stars in Gemini should be rising directly behind their back.
And it wasn't just about the stars either. He also factored in the wind.
He did.
He stated that the east wind should be blowing against your left shoulder and the west wind should be hitting your right cheek.
Right. So when you synthesize all of those physical inputs, the stars at your ear and back, the wind on your shoulder and cheek, you are essentially forcing the individual to face the direction of the winter sunset in that specific geographic region.
And by aligning with that winter sunset, you are facing Mecca.
According to Ibn Suraka, that orientation ensured the believer was facing the northeastern wall of the Kaaba.
It is such a brilliant, entirely bodily orientation to the physical world.
It requires no equipment, just an intimate knowledge of the local sky and weather patterns.
Okay, but I have to push back on the scalability of this.
Go ahead.
If I am navigating a modern city and someone tells me to walk until the wind hits my left shoulder, I am going to end up completely lost the moment the weather changes.
That is a very fair point.
I mean, the wind shifts, the stars alter their positions slightly over the centuries due to precession. While I understand this works for a local farmer who intimately knows his valley, how does this function on a macro level?
It really doesn't.
Right, like how does a sprawling intercontinental civilization rely on localized winds and the feeling on your cheek to orient itself?
You are hitting on the exact limitation of folk science. It was subjective and it was deeply localized.
So why did it stick around?
To understand why it persisted, we have to look at the conceptual framework it supported, which is known as sacred geography.
Sacred geography. Okay, break that down for us.
In this model, the goal was not to draw a perfectly scaled map of continents. The goal was to visualize the entire inhabited world as a massive circle, with the Kaaba sitting squarely in the center.
And the Kaaba itself is a roughly rectangular structure.
Right. And medieval scholars conceptually projected its four walls outward to the edges of the known world, dividing the Earth into distinct sectors.
The sources show diagrams of this. Some scholars divided the world into 4 sectors corresponding to the 4 walls.
Yes, but others got highly detailed, breaking the world into 8, 12, or even 72 different sectors radiating out from the center.
72 sectors. That is incredibly detailed.
The detail in those 72 sector models is truly extraordinary. Scribes would draw these circular diagrams in treatises on sacred law.
What do they look like?
You would see the Kaaba at the hub and the various regions of the Islamic world arrayed around the rim.
Give me an example.
For instance, the entire region between northwestern Africa and northern Syria was conceptually tethered to the northwestern wall of the Kaaba.
Okay.
The lands stretching from Armenia all the way to Kashmir were linked to the northeastern wall.
And what about the south?
The Yemen was associated with the southern corner. It was a conceptual map that prioritized spiritual orientation over physical distance.
So if I am living in Kashmir, my mental map of the world is defined by my relationship to that specific northeastern wall.
Precisely. Sacred geography provided a profound sense of unity.
Because everyone is facing the same center.
Exactly. No matter how far the empire expanded, every citizen was geometrically anchored to the exact same point.
That makes sense for daily prayers.
Yeah.
But getting back to my earlier critique about scalability, a localized bodily orientation helps a person pray, but it seems completely useless to an imperial administrator.
Oh, it is entirely useless for administration.
Right. If you are the caliph in Baghdad and you need to dispatch a courier to Egypt or calculate the agricultural tax yield of a province in Persia, you cannot rely on the stars of the Great Bear.
No, you cannot. You need actionable, empirical data about roads, borders, and distances.
You need a completely different kind of map.
And that exact need burst an entirely new school of thought.
Which means we have to move from the realm of the sacred to the realm of the bureaucratic.
Yes. The need for administrative control brings us to a specific intellectual movement in the 10th century known as the Balkhi School.
The Balkhi School.
This marks a pivotal shift in how the physical world was recorded. It was founded in Baghdad by a Persian polymath named Abu Zayd Ahmad ibn Sal al-Balkhi.
He was born around the year 850, correct?
That is correct. And Baghdad at this time was the administrative and intellectual heart of the Abbasid Caliphate.
Which was a massive bureaucratic machine.
A huge machine.
Yeah.
So al-Balkhi and the scholars who followed his methods, most notably al-Istakhri and al-Muqaddasi, were not trying to map the cosmos.
They had a highly specific utilitarian agenda.
Extremely specific.
And the records indicate they exclusively mapped the Islamic world.
Yes, which they referred to as Mamlakat al-Islam.
They divided the empire into about 20 distinct climes or provinces. But what stands out to me is that they deliberately ignored the non-Islamic world.
They did.
They essentially cropped the map to only show their own borders.
They were really the first to systematically employ geographic boundaries to differentiate one political province from another.
Because before this, maps often flowed without clear delineations of where one jurisdiction ended and another began.
Exactly. The Balkhi school maps are distinct precisely because they are administrative tools.
And the physical appearance of these maps is also incredibly distinct.
Very much so.
Researchers have studied surviving manuscripts from this tradition, particularly a group of texts known as the Ottoman cluster. Can you explain what these maps actually look like? Because they do not look like the maps we use today.
Not at all. They are highly stylized, almost to the point of abstraction.
In what way?
Well, the surviving manuscripts are drawn on very thin, highly polished paper. The text is written in a tight Nosky script.
Nazki is a cursive script, right?
Yes, it is a highly legible Arabic script that was developed for speed and clarity, which is exactly what an administrator copying documents would need.
That makes sense.
Interestingly, these specific maps often lack diacritical marks, the dots that distinguish different letters in Arabic.
Oh, really? Why would they leave the dots out?
It suggests they were meant to be read by highly educated individuals who already knew the names of the places through context.
Wow, okay. But the geography itself is abstracted too, right?
Highly abstracted. They did not try to draw the jagged, realistic coastline of a sea or the winding path of a river.
Right, the lines are strictly geometric.
Yes, a river is drawn as two perfectly parallel lines.
And the lake is just a flawless circle.
Exactly. And the cities are not depicted as sprawling urban centers. They are represented by simple symbols like squares, circles, or four-pointed stars,
And south is always positioned at the top of the map.
with Mecca located near the center. This orientational south at the top became a standard convention for Muslim cartographers.
It is such an extreme geometric abstraction.
It is intentional, though. Think about when you are looking at a subway map today. You do not care about the exact geographical curve of the train tracks.
Right, you only care about the sequence of the stops and how the different lines intersect.
Exactly. The Balkhi maps function similarly. They eliminated all unnecessary geographical noise to highlight the network of provinces.
It is the ultimate pragmatic approach.
It really is.
But this system wasn't static. The information on these geometric maps was constantly being updated by people actually moving through the empire.
Yes, which introduces one of the most significant figures of the era, Ibn Hawqal.
Even Hawqal, he was a 10th century merchant and geographer, right?
Yes, and unlike scholars who spent their lives in the libraries of Baghdad translating Greek texts, Ibn Hawqal was physically out in the world
But traveled extensively.
for 30 years, from roughly 943 to 973.
That is a long time to be on the road.
His journeys took him through North Africa, Islamic Spain, Egypt, Armenia, Iraq, and even the island of Sicily.
He essentially ground-truthed the empire.
He absolutely did.
I read that during his travels in the Indus Valley, he actually crossed paths with al-Istakhri, one of the leading geographers of the Balkhi School.
Yes, they met.
And that meeting seems to have sparked something, because Ibn Hawqal took those abstract, geometric Balkhi maps and fundamentally upgraded them.
He layered those administrative maps with vital socioeconomic data.
Because a perfectly circular lake and a square city is helpful for a bureaucrat. But Ibn Hawqal added the information a merchant actually needed.
Exactly. He recorded detailed estimates of provincial tax revenues in dinars
He documented the local irrigation systems.
and agricultural yields. But most importantly, he mapped the specific caravan routes connecting these cities.
And he measured those routes using a unit called the farsakh.
Yes.
Can you explain the farsakh?
The farsakh is derived from an ancient Persian unit of measurement. It is roughly equivalent to the distance a laden camel can walk in a single hour.
Which is about 3 to 3.5 miles.
Correct. By marking the caravan routes in farsakhs, Ibn Hawqal provided an incredibly practical tool for calculating travel time and logistical supply needs.
But Ibn Hawqal did something much more significant than just calculate travel times.
He did. His physical presence in these regions allowed him to challenge a deeply entrenched scientific dogma.
He directly contradicted the classical Greek theories of Ptolemy.
Right. The Greek geographical tradition, inherited primarily from Ptolemy's works in the 2nd century, proposed a concept of climatic zones.
How did those zones work?
Ptolemy posited that the Earth was divided into bands of latitude. The northern bands were too cold to sustain life, and the equatorial and southern bands, the torrid zone, were so scorched by the sun that they were completely uninhabitable.
And that theoretical model had been accepted as absolute truth for centuries.
Yes, no one really questioned it in the scholarly community.
But Ibn Hawqal actually traveled south.
He journeyed deep into sub-Saharan Africa and along the East African coast bordering the Indian Ocean.
And he did not find a scorched, uninhabitable wasteland.
Not at all. He found thriving populations, complex societies, and extensive trade networks.
So he proved the classical texts wrong through direct empirical observation.
He prioritized what he saw with his own eyes over the speculative philosophies of antiquity,
And he integrated his demographic and commercial observations into his spatial analyses.
proving that human habitation extended far further south than previously believed.
Okay, but this brings me to a major point of friction.
What is that?
Ibn Hawqal travels the world. He proves that the southern regions are inhabited.
Yes,
He knows that lucrative trade routes extend into Europe and eastward toward China.
he does.
Yet he maintains the core philosophy of the Balkhi School.
Yeah.
He still intentionally crops his maps to only show the Islamic world. Why?
It is a good question.
I mean, if you have just revolutionized the understanding of the globe's habitable zones, why continue to draw a map that ignores the rest of the planet?
Well,
It feels like looking at a corporate flowchart. The chart shows human resources, accounting, and marketing because that is all the CEO cares about. It completely ignores the existence of rival companies or the outside market.
that corporate flowchart analogy is exactly right, actually. Yes. The bulky maps, even with Ibn Hawqal's extensive revisions, were never intended to be universal maps of the cosmos.
They were just internal documents.
They were specific tools designed for the internal management of a specific entity. The Islamic Empire at this time was arguably the most complex administrative state on Earth.
The logistics must have been a nightmare.
The challenge of merely managing the internal postal routes, the tax collection, and the movement of the military was all-consuming.
So they mapped the Mamlakat al-Islam because that was the boundary of their administrative reality.
They mapped what they had the power to control.
It makes a lot of practical sense.
However, while the Balkhi School geographers in Baghdad and Persia were focusing inward, creating these highly pragmatic, internally cropped maps, an entirely different intellectual movement was happening simultaneously.
Right. Other scholars working in different political centers found the cropped nature of the Balkhi maps deeply unsatisfying.
Very unsatisfying. They wanted to understand how their empire fit into the wider universe.
They wanted to capture the entirety of the known Earth on a single page.
And that ambition takes us away from the Abbasid court in Baghdad and moves us westward.
To the rival Fatimid Caliphate in Egypt.
Exactly, sometime between the years 1020 and 1050.
The Fatimid court in Cairo was a vibrant intellectual hub.
It actively competed with Baghdad. And it is here that an anonymous author produced a truly massive encyclopedic manuscript.
Known as the Book of Curiosities of the Sciences and Marvels for the Eyes.
Yes,
This document is really something because it was essentially lost to history for centuries.
it was.
The physical manuscript that scholars study today is actually a 13th century copy of the 11th century original.
Yes, and it was acquired by the Bodleian Library at Oxford University in 2002.
The level of detail we have regarding its physical construction is incredible.
The physicality of the manuscript provides a really great window into the material culture of medieval science.
It is a big book, isn't it?
It consists of 46 folios.
Which means 96 pages.
Right, and each page measures 324 by 245 millimeters.
That is a substantial ledger-sized book.
But what really stands out is the paper itself. It was produced using a grass mold process.
Can you explain why that specific detail matters? Why is the type of paper significant to the history of cartography?
Well, the adoption of paper is one of the most critical technological leaps in this era.
Because before paper, what did they use?
Texts were written on parchment or vellum.
Which are made from animal skins.
Yes. Parchment is incredibly durable, but it is enormously expensive and resource-intensive to produce.
Right, a single large book could require the skins of an entire herd of sheep.
Exactly.
Yeah.
But the Islamic world acquired paper-making technology from China in the 8th century and rapidly refined it.
And this grass mold process.
It involves suspending plant fibers in water and using a screen made of woven grasses or reeds to lift a layer of pulp.
Which is then dried.
Right. This created a sturdy, light, biscuit brown paper that was vastly cheaper and easier to produce than parchment.
So cheaper material means you can produce more books.
Yes.
Which means knowledge spreads faster.
Exactly.
Okay.
The proliferation of affordable paper facilitated an explosion of scientific writing, translating, and map making.
And the copyists of the Book of Curiosities really utilized this material masterfully.
They did. They used a dense, opaque black ink for the main body of the text.
And they reserved a striking red ink for the headings to organize the massive amount of information.
Yes, and the illustrations themselves are like works of art. The manuscript contains 17 maps.
And the creators actually dusted gold or silver flakes onto the wet paint.
To represent comets in the astronomical sections and islands in the geographical sections.
They also used tarnished silver to depict the curved, sweeping areas of water.
And an oxidized lead red paint to vividly represent the land masses.
The structure of the book is highly methodical, too. It is divided into two distinct halves.
Book 1 is dedicated to the heavens.
Over 10 chapters, the author details the mechanics of astronomy.
the paths of comets, and the movements of the 5 visible planets.
And then Book 2 brings the focus down to the Earth, spanning 25 chapters.
Book 2 contains highly specific regional maps, the Indian Ocean, the Mediterranean, the Caspian Sea.
And detailed river maps of the Tigris, Euphrates, and the Nile.
But the absolute centerpiece of the entire manuscript, taking up the entirety of the 2nd chapter, is a standalone rectangular map of the world.
This rectangular map is a monumental artifact.
It is widely considered the earliest surviving map to feature a graphic scale bar prior to the European Renaissance.
What exactly is a graphic scale bar in this context? Are we talking about the lines of latitude and longitude?
Yes, essentially a graticule. The presence of this mathematical grid across the top of the map indicates a profound shift.
Because the Balkhi maps we discussed earlier were schematic.
Right. They showed relative connections without strict adherence to physical distance.
So the inclusion of a scale bar means the author of the Book of Curiosities was attempting to map the world onto a mathematically precise coordinate system.
It shows a deep familiarity with the cartographic systems of Greek antiquity, specifically the coordinates developed by Ptolemy.
Though the author flipped the traditional Greek orientation,
Yes, Ptolemy put north at the top, but this map places south at the top.
adhering to the Arabic cartographic convention. And the map is incredibly dense with data.
Very dense.
The author populated the land masses with 395 specific city names and trade routes.
All represented by distinct red dots.
This is where the intersection of different knowledge systems becomes apparent. The author of this Fatimid manuscript did not travel to all 395 cities.
No, they pulled that data from earlier texts.
Specifically, those red dots, representing cities and caravan routes, were extracted directly from the empirical work of Ibn Hawqal.
Yes, they were.
Okay, but here is where I see a massive glaring contradiction.
Let's hear it.
We just established that Ibn Hawqal, through his decades of physical travel, empirically proved that the southern regions like sub-Saharan Africa were populated, thriving, and deeply connected by trade.
That is correct.
The author of the Book of Curiosities is literally looking at Ibn Hawqal's data. They're using his red dots to mark the map.
Right.
Yet, on this highly detailed rectangular map of the world, well, the entire continent of Africa is completely missing.
It is entirely omitted.
How does that happen?
Well,
The author deliberately left Africa out because they believed it was uninhabited, which is a reversion back to the old, disproven Greek theories of Ptolemy.
yes.
How can a highly educated scholar sit in Cairo, read the empirical proof from Ibn Hawqal that the south is inhabited, use Ibn Hawqal's data for cities in Iraq and Persia, but then completely ignore his data regarding Africa? It is immense cognitive dissonance.
It really is. But it highlights the deeply fragmented, siloed nature of medieval knowledge.
So they weren't seeing the whole picture.
We often assume that once a scientific breakthrough is made, it instantly replaces the old paradigm everywhere. But that is rarely true.
Right.
An author sitting in a library in Fatimid Egypt had access to a vast array of texts from different eras and different cultures.
They cite over 20 different written sources in the manuscript.
Exactly. They were receiving geographical knowledge flowing from Syriac-speaking scholars, translated pre-Islamic Greek texts, and contemporary Arabic merchant accounts.
So they are essentially trying to build a puzzle using pieces from 5 different puzzle boxes.
That is a perfect way to describe it. The author valued Ibn Hawqal's administrative data for the Central Islamic lands because it was highly accurate.
But when it came to the overarching shape and habitability of the entire globe,
The intellectual gravity of Ptolemy and the classical Greeks was still overwhelmingly powerful.
they were synthesizing texts, but they were not necessarily reconciling the inherent logical contradictions between a 2nd century Greek theory and a 10th century merchant's travelogue.
Exactly.
It shows the limitation of relying entirely on compiling texts. If Book A says the world is shaped one way and Book B says it is shaped another, sitting in a library reading both books will not solve the problem.
No, it won't. To resolve these massive discrepancies about the fundamental shape, scale, and layout of the Earth, a new generation of scholars realized they had to move beyond textual synthesis.
They could no longer rely on traveler anecdotes or ancient philosophy.
They had to go out into the physical world and mathematically measure the Earth itself.
Which brings us to the quest for absolute mathematical precision.
The search for hard data.
If you want to draw an accurate map of the globe, you need a coordinate system. Determining a city's latitude, its position north or south of the equator, was relatively straightforward, right?
Fairly straightforward, yes. You measure the angle of the pole star or the maximum elevation of the sun.
But determining longitude, a city's position east or west, was the supreme geographic challenge of the era.
The longitude problem is fundamentally a problem of time.
Time. How does time give you distance?
To find the difference in longitude between two cities, you have to know the exact difference in their local times when a specific event occurs.
Okay.
The Earth rotates continuously. If it is noon where I am, and it is 2 hours past noon where you are, we can calculate the distance between us.
But to do that, we need perfectly synchronized clocks.
Which they didn't have.
Right, in the 10th century, nobody had an accurate portable clock. You could not synchronize a water clock in Baghdad, load it onto a camel, travel for a month to Central Asia, and expect it to still keep perfect time.
The jostling, the temperature changes, the evaporation, it would completely ruin the mechanism.
So without a mechanical clock, synchronizing time across thousands of kilometers of rugged terrain was seemingly impossible.
Which is why they had to look up.
They had to use the cosmos as their clock.
Exactly. This sets the stage for one of the most notable scientific experiments of the medieval period occurring in the late 10th century.
We have two Persian scholars involved in this.
Yes.
In the city of Khwarezm, which is located in modern-day Uzbekistan, we have Abu Rahan al-Biruni.
He was a brilliant young polymath, only 24 years old at the time.
And over 1,000 miles away, in the imperial capital of Baghdad, we have Abu al-Wafa al-Buzjani,
who was a 57-year-old, highly established astronomer and mathematician.
These two men managed to coordinate a synchronized astronomical observation across a massive distance.
They corresponded by letter, which meant their messages took weeks or months to travel via caravan to agree on a specific celestial event to observe.
And on the night of May 24th, 997, they both went out to observe a lunar eclipse.
A lunar eclipse is the perfect mechanism for this experiment.
Why a lunar eclipse specifically?
Well, unlike a solar eclipse, which is only visible along a narrow path on the Earth's surface and occurs at different local times for different observers.
A lunar eclipse occurs when the Earth's shadow falls across the moon.
Exactly. It is a singular, objective event in space. Anyone on the night side of the Earth who can see the moon sees the eclipse happening at the exact same absolute moment.
So, al-Biruni is standing in Khwarezm.
Right.
And al-Buzjani is standing in Baghdad.
Right.
They are both watching the moon. They carefully recorded the exact local time based on the stars when the Earth's shadow first touched the moon.
And when the moon was fully covered and when the shadow receded.
When they eventually exchanged their notes months later, they compared their localized timings.
They determined that the local time difference between the eclipse occurring in the sky over Khwarezm and the eclipse occurring in the sky over Baghdad was exactly 1 hour.
Okay, walk me through the math here. How does a 1-hour time difference translate into physical distance on a map?
It relies on the geometry of a sphere. The Earth rotates a full 360 degrees in a 24-hour period.
Right.
If you divide 360 by 24, you get 15.
So 15 degrees per hour.
That means the Earth rotates exactly 15 degrees of longitude every single hour. Because the local time difference between the two scholars was 1 hour, they could mathematically conclude that the longitudinal difference between Baghdad and Khwarezm was 15 degrees.
That is incredibly elegant. They successfully measured the exact distance across more than 1,500 kilometers of mountains and deserts without ever laying down a measuring chain.
And they achieved an error rate of only 7 to 8% compared to modern satellite data.
It was a direct, accurate measurement that entirely bypassed the old methods of estimating distance based on how many days a caravan took to walk between cities.
Which was always flawed because caravans take winding paths, stop for weather, and travel at different speeds.
But al-Biruni did not stop at finding longitude. He was obsessed with geodesy,
which is the applied mathematics of measuring the Earth's exact shape and size.
Years later, he was residing at a fortress in Nandana, located in the Punjab region of present-day Pakistan.
Yes.
There, he devised a method to calculate the absolute radius of the entire planet. And he did it using trigonometry.
Al-Biruni's method at Nandana is a masterpiece of geometric reasoning. First, he needed a baseline.
So he went to a vast, perfectly flat plain near the fortress.
And he measured the exact height of a prominent, sheer hill rising out of that plain.
How did he do that without just dropping a rope from the top?
He did this by measuring the angles to the top of the hill from 2 different points on the flat ground using an astrolabe.
And then applying the trigonometric functions of sine and tangent.
Exactly.
So now he has the precise height of the mountain. What does he do next?
He climbed to the very summit of that mountain. Looking out over the perfectly flat horizon, he used his astrolabe to measure the angle of the dip of the horizon.
Let me make sure I understand this.
Yeah.
If you are standing on a perfectly flat plane, your line of sight to the horizon is essentially level. But if you go up high on a mountain, you actually have to look slightly downward to see where the sky meets the Earth, because the Earth is curving away from you.
That downward angle is the dip.
Correct. Al-Biruni measured that tiny angle of depression.
Now he had a right-angled triangle.
He knew the height of the mountain,
He knew the angle of the dip.
and he knew that a line drawn straight down from his feet would eventually hit the exact center of the Earth.
Yes. So, using complex algebra and trigonometric formulas, he calculated the radius of the Earth based solely on those physical measurements.
The numbers he produced are unusual in their accuracy. He calculated the radius of the Earth to be 3,928.77 miles.
Which is incredibly close.
Today, using lasers and satellites, we know the actual mean radius of the Earth is 3,847.80 miles. His calculation, done on a hilltop in the 11th century with a brass instrument, was only 2% higher than the modern value.
It is a profound achievement.
But I have to ask the skeptical question.
Let's hear it.
Did he truly devise a flawless mathematical calculation, or did he just get lucky with his numbers?
He absolutely did not get lucky with the geometry. His mathematical formula was pristine and theoretically perfect.
But he was off by 2%.
Yes, because the physical environment of the planet introduced an optical illusion that he could not see, and that is where the 2% error originates.
What kind of optical illusion?
Atmospheric refraction.
Ah,
The Earth's atmosphere is not empty space. It is filled with air of varying temperatures and densities.
right. And light bends when it goes through different densities.
As light travels through the atmosphere, it bends. When you stand on a mountain and look at the horizon, the light from the horizon is actually curving slightly over the curvature of the Earth.
So the horizon looks higher than it actually is.
Exactly. This refraction alters the measured dip angle by about 1/6 of its true value.
So al-Biruni's mathematical geometry was flawless. But the physical atmosphere bent the light and slightly skewed the raw data entering his astrolabe.
He had the math completely perfected, but the field of atmospheric physics had not yet advanced enough to tell him he needed to correct the raw optical data.
It really shows us the absolute bleeding edge of medieval capability.
It does.
Despite that slight refraction error, the methods developed by al-Biruni and his contemporaries were revolutionary. Across the empire, scholars were using these techniques to calculate rigorous, mathematically sound coordinates for hundreds of cities.
But having a massive list of raw data coordinates is not the same thing as having a map.
Right. The data existed, but it was scattered in manuscripts across different cities.
To turn that raw mathematical data into a unified, definitive map of the known world, you need two things.
You need a visionary patron with enough money to fund the project.
And you need a master synthesizer capable of putting all the pieces together.
That monumental synthesis finally occurred in the middle of the 12th century, in the year 1154.
And interestingly, it did not happen in Baghdad or Cairo.
No, it happened in the court of Norman Sicily, under the patronage of a Christian monarch, King Roger II.
King Roger commissioned a Muslim geographer named Muhammad al-Idrisi to create a comprehensive map of the world.
Al-Idrisi had a fascinating background.
He was born in Ceuta, a city in North Africa, and he was educated in the great intellectual center of Cordoba in Islamic Spain.
He spent 15 years residing in the Sicilian court, painstakingly compiling a work titled Nuzhat al-Mushtaq fi Itirak al-Afaq.
The title eloquently translates to the excursion of the one who yearns to penetrate the horizons.
Al-Idrisi's approach was fundamentally different from the fragmented manuscript traditions we discussed earlier.
He utilized a highly structured mathematical grid system to organize the data.
He divided the entire northern hemisphere into 70 distinct uniform sections.
How did he organize that grid?
He started with the concept of latitudinal climates. He divided the hemisphere horizontally into 7 broad climes, stretching from the equator to the northern ice. Then he divided each of those 7 horizontal climes vertically into 10 longitudinal sections.
So 7 times 10 gives you 70 uniform sectors covering the known world?
Exactly. It provided an organized framework to slot in the vast amount of data being collected.
And the physical manifestation of this data is really significant. It was not just a paper book.
No, King Roger wanted a monument. The map was meticulously engraved onto a massive, solid silver disc.
This silver map was 6 feet in diameter and weighed 450 pounds.
The choice of silver is significant, isn't it?
It is incorruptible, it represents immense wealth, and it is soft enough to engrave with incredibly fine detail.
Upon one side of this massive disc, the zodiac and the celestial constellations were engraved.
And upon the other side, the entire known geography of the Earth, the bodies of land, the sweeping coasts, the rivers, the mountain ranges, was detailed.
This 450-pound silver disc was also accompanied by a text containing 70 paper maps corresponding to the grid sections.
The level of detail achieved in the Tabula Rogeriana, as it became known in Europe, was unprecedented.
It accurately depicted the dual sources of the Nile River deep in Africa.
It mapped the coast of Ghana.
It even extended far into northern Europe, including mentions of Norway.
What makes al-Idrisi's work so reliable is his rigorous methodology.
He did not just sit in the royal library compiling old Greek texts and copying Ibn Hawqal's dots.
No, the records detail how he and the scholars of the Sicilian court actively gathered fresh intelligence.
Because Sicily was a massive maritime hub.
Exactly. When merchant ships docked, al-Idrisi and his team would interview the travelers.
And they had a specific process for filtering those interviews to weed out exaggerations and tall tales.
They would cross-reference accounts from different sea captains and caravan leaders who had never met each other.
If multiple independent sources reported the exact same geographical feature, the same distance, or the same coastal shape, al-Idrisi would document it.
But if a report conflicted or could not be corroborated by a separate source, they ruthlessly threw the information out.
It was an early form of rigorous peer review applied to geography.
It absolutely was.
But I want to pause and look at the cultural dynamic here because it is remarkable.
It is.
You have a Muslim geographer born in North Africa, educated in the sophisticated academies of Islamic Spain.
Yes.
He is utilizing complex longitudinal data calculated by Persian astronomers in Baghdad.
Yes.
And he is bringing all of this together to build a 450-pound silver map for a Christian Norman king on an island in the middle of the Mediterranean.
Right.
How did this deeply collaborative, cross-cultural scientific environment exist amidst the broader political and religious conflicts of the 12th century?
It really demonstrates a fundamental truth of the medieval Mediterranean. Knowledge was the ultimate currency.
Knowledge as currency.
Accurate geographic information was not just academic, it was strategic. It was vital for controlling trade routes, for achieving naval dominance, and for projecting royal prestige.
And King Roger II recognized that the scholars of the Islamic world possessed the most advanced geographic data and mathematical tools on Earth.
And King Roger possessed the immense wealth and the stable political environment necessary to synthesize it.
So the court of Sicily functioned as a unique melting pot where Greek, Latin, and Arabic cultures intersected.
Because the king prioritized scientific utility over political boundaries.
The resulting silver map is a monumental achievement of synthesis.
It is.
But here's the practical problem. While a 6-foot silver disc is a beautiful centerpiece for a royal throne room, it is completely useless to a sailor out on the open ocean.
Completely useless. You cannot load a 400-pound piece of silver onto the deck of a pitching dhow in the Indian Ocean to figure out where the nearest port is.
So this vast, synthesized geographical knowledge had to be miniaturized.
It had to be translated from theoretical cartography into practical navigation.
And the scholars of the Muslim world refined several physical instruments to solve this problem of miniaturization.
The astrolabe is perhaps the most famous.
It was first constructed in the Islamic world by a mathematician named Muhammad al-Fazari in the 8th century.
And it was continuously refined over the centuries.
The astrolabe is essentially a two-dimensional projection of the three-dimensional night sky.
Right. Muslim astronomers heavily modified the early Greek designs. They introduced complex angular scales and inscribed circles indicating azimuths on the horizon plates.
Azimuths?
Which denote the direction of a celestial object from the observer.
Ah, okay.
So it became an incredibly versatile analog computer, widely used to navigate by the stars, tell time, and importantly, to calculate the direction of the Qibla.
But the sources also focus on a much more specific, seemingly simpler tool, the magnetic compass.
Yes.
So you look at a text written by an astronomer named al-Ashraf, who was working in Yemen in the 13th century.
He provided a highly detailed description of how to construct a magnetic compass for navigation.
The properties of magnetism were known, but al-Ashraf's text detailed its specific application for geographic orientation.
He described taking a bowl and filling it with water. Then, the user takes a light rush-like stem and places it so it floats on the water surface.
And a magnetized iron needle is carefully inserted so it intersects with the floating stem.
He notes that the intersection must be positioned precisely over the center of the bowl to allow for free movement.
And as the stem floats, the magnetic needle naturally aligns itself with the Earth's magnetic field.
The head of the needle represents the north point.
But Al-Ashraf did not just tell people to look at the needle and sail north.
No, he integrated this physical tool with advanced mathematics. To use the compass accurately, a navigator had to consult a complex mathematical table known as the Jadwal Ishrini.
The Jadwal Ishrini translates to the 20 by 20 table.
It was a grid containing 400 specific mathematical entries.
These entries calculated the exact deviation of the Qibla for different latitudes and longitudes.
It was essentially a printed algorithm. By consulting this lookup table, Al-Ashraf calculated that the Qibla for a person standing in central Yemen was exactly 27 degrees east of north.
So he instructed the user to look at the floating needle to find north, and then meticulously count 27 degrees along the rim of the bowl eastward.
That specific line gave the exact mathematically proven direction of Mecca from central Yemen.
Furthermore, as they used these magnetic needles more frequently, Islamic astronomers began to understand the concept of magnetic declination.
They realized that the physical reality of magnetic north, where the needle points fluctuates and actually differs slightly from true geographical north, derived from the stars.
And by the 15th century, an Egyptian astronomer named Al-Aziz Al-Wafa had measured this specific magnetic deviation at precisely 7 degrees from the city of Cairo.
They were constantly refining the physical tools to match the mathematical reality.
I have to pause and ask about the trajectory of all this, though.
Okay.
We started with the visceral, physical feeling of the wind on your cheek. Then we discussed incredibly complex mathematical maps, the advanced trigonometry of calculating the Earth's radius on a mountain in Pakistan, and grids dividing the hemisphere into 70 distinct sections.
Yes.
And now, at the end of this evolution, we're talking about a guy pushing a piece of metal through a reed and floating it in a bowl of water.
I see where you're going.
How does a floating needle compete with a 400-pound silver map? Isn't this just a step backward into the folk science we started with?
It might look simpler in its physical construction, but it is absolutely not a step backward. The compass did not replace the advanced mathematics. It was the mechanism that applied the math.
Okay, applied it how?
The instrument allowed a common sailor or a traveling merchant to physically access the incredibly complex coordinate grids calculated by scholars like al-Biruni and al-Idrisi.
So the math was hidden in the tables.
Yes. The Jadwal Ishrini table contained the high-level theoretical geodesy. The bowl of water and the magnetized needle were simply the display interface.
So it's the hardware running the software of the mathematical maps.
Precisely. It allowed a human being to access theoretical geodesy while standing on the deck of a ship in the dark, or resting at an oasis on a trade route.
It brilliantly bridged the gap between the isolated scholar doing trigonometry on a mountain and the practical merchant moving goods across the globe.
It is the ultimate democratization of data.
The immense intellectual effort required to measure time across vast deserts by synchronizing eclipses, to calculate planetary distance using the dip of the horizon, and to find the precise, unerring direction to face the Kaaba. All of that labor laid the conceptual groundwork for how we navigate today.
It really did.
Every time you open a map application on your phone, the invisible mathematical grid system guiding you, the calculation of your exact coordinates relative to your destination, is a direct descendant of these exact medieval struggles to map the Earth.
The desire to orient oneself accurately in the physical world is a profound driver of scientific innovation.
Whether that drive originates from a religious duty to pray, an imperial need to collect taxes, or a merchant's need to navigate an ocean. And as we conclude, I want to leave you with one final, deeply provocative concept to mull over.
Oh, this is a good one.
We talked extensively about Abu Rayhan al-Biruni, the scholar who calculated the radius of the Earth with staggering accuracy.
Yes, the mountain in Pakistan.
Based on his incredibly precise measurements of the planet's circumference and his knowledge of the total size of the interconnected landmass of Africa, Europe, and Asia, al-Biruni realized the numbers did not add up.
The known landmass was too small to account for the entire surface area of the globe.
Purely through mathematical reasoning and geometry, in the year 1037, al-Biruni deduced that the vast, seemingly endless ocean separating the western edge of Europe from the eastern edge of Asia must contain other undiscovered, substantial, and likely inhabited landmasses.
He had no physical proof.
He had never sailed the Atlantic.
He simply trusted the data.
Purely through geometry, he deduced the existence of the Americas nearly 5 centuries before they were mapped by European explorers.
It is incredible.
It forces you to wonder, what other entirely logical deductions are sitting quietly in our modern data sets, just waiting for someone to put the mathematical pieces together? Thank you for listening. History Maps. Learn history visually.